Okay, in this video, I'm going to talk about the problem of one and two tail tests. I'm going to do this via example and using some graphing technology. So this should be, hopefully, by the end of this, you'll understand the difference. So let's start with my research hypothesis. Children in a randomly selected sample eat more Halloween candy in ounces than a sample as a whole, than the population as a whole. Here's our null and our alternative hypotheses. So our null hypothesis is that children in a randomly selected sample do not eat more Halloween candy than the population as a whole. So that's just your average null hypothesis. This is the one you want to reject. So in this lecture video, we're talking about alternative hypotheses because this is where the one or two tail testing comes into play. Let's start with directional hypotheses. These are also known as one tail tests. We'll start with the right tail directional hypothesis. We'd say children in a randomly selected sample eat more Halloween candy than the population as a whole. So it's directional. So we're talking about the direction of the relation. They eat more is greater than, right? So here are our alternative hypothesis. I'll write this as H sub 1 is our mean is greater than, our sample mean is greater than our population mean. Population mean is written as mu for population, and samples using Latin letters with a bar. Greek letters are generally used for population values. And our left-tailed alternative would be, a left-tailed alternative would be that children in a randomly selected sample eat less Halloween candy than the population as a whole. So here we have the sample mean is less than the population mean. This would be our non-directional hypothesis. Our non-directional hypothesis would state, and this is the one we call a two-tail test, because now we're looking at, so we'll look at the distribution in a second. This distribution looks like a bell for the standard normal distribution. It looks like a bell. It's a bell-shaped curve and has these tails that extend to negative and positive infinity. So it goes in two different directions. So that's why we call it a two-tail test. And it's non-directional because I'm not stating a direction in the relation. And this is generally done when I'm not really sure. We usually do this a priori before we collect our data, so we're not always sure. Sometimes we are, and when we are, we'd like to say so by doing a one-tail test. But when we're not sure, sometimes it's better to just go not directional. So in this example, we have children in a randomly selected sample do not eat the same amount of candy, Halloween candy, as the population as a whole. So here I said, I didn't say whether they eat more or less. I said it's just going to be different. Okay, let's make an assumption that we select our type 1 error rate, the probability of a false positive result, also known as alpha. We use this Greek symbol alpha to denote the type 1 error probability. We'll select it to be 0.05. This is a very standard probability of a type 1 error. And what this means is that we accept a chance of a false positive rate being 5% or less. So we can be wrong. I mean, we're not always going to be 100% correct. So, but how wrong is it okay to be? So we'll say, oh, it's okay to be wrong 5% or less of the time. So that means we will accept any probability of less than or equal to 0.05 as indicative of a significant difference between our sample and the population. So that's what the type 1 error rate or alpha means. Okay, so imagine that now let's break this down a little bit. Imagine that our alternative hypothesis is right directional. So we propose that our sample mean will be greater than the population mean. And we find our sample mean is 4.7. Remember, our population mean was 4. Let's say we have a sample of n equals 25. So 25 individuals in our sample. So what's the probability that our sample mean is greater than the population mean? So we calculate our z-test statistic. So this isn't a lecture on z-test statistics, so I'm assuming you already understand how to do this. So we calculate our z-test statistic. This is bottom is our standard error, and we get 1.75. We get 1.75. So our question is, oops, let's change that. Our question is, what is the probability that our z value is greater than or equal to 1.75? And again, this is a right tail test that's directional in the right direction. because this is positive. So this can be rewritten as what's the probability that z is greater than or equal to 1.75. And I used a calculator and I found this to be 0.0401. And if you look at this, this represents the right tail of this distribution. So any value in this purple area here has a probability of 4.01 or lower, right? So it has a really small probability. You always say given the null hypothesis is true. So given the null hypothesis is true, a z-value of 1.75 or greater has only a probability of 0.0401, and that's what's represented in this area here. Everything below this is 1 minus that value, right? So it's 0.96, basically. Okay, but this is really key, saying that given the null hypothesis is true, because we're saying what's the probability of a result this extreme or more extreme? What's the probability of finding something like that given the null hypothesis is true? And it's very, very, very low, right? So it's only 4%, basically. So given that our p-value is less than or equal to 0.05, that's our alpha. So that's, remember, we said we can accept being wrong 5% of the time or less. We would reject the null hypothesis that our sample mean is equal to the population mean, right? Because so the probability of our result is pretty small if the null hypothesis is true. So let's assume that the null hypothesis is true. That's telling us that our sample is actually part of this population, right? But it's just an extreme value. We got these kids who eat a lot of candy, right? So, but they're not really outside of this population. They're just like on the fringes of the population. So if I conclude that they don't belong to this population, I am wrong. But the probability of me being wrong is very small. It's only 4%. And I said I don't mind being wrong 5% or less. So that's what it means to statistically reject the null hypothesis. I'm okay with being wrong that small amount of time. All right, let's do the left side alternative hypothesis. And again, it's directional. We propose that our sample mean will be lower than the population mean. We find that our sample mean is 3.3 ounces. So these kids ate less candy than the population mean. And assuming that our sample size is again 25, what's the probability that our sample mean is lower than the population mean? We calculate our z-test statistic result, and now it's minus 1.75. Now, of course, I purposefully made these equal, either 1.75 or minus 1.75. Not always going to turn out to be that way, right? Our question becomes, what's the probability of a z-value less than or equal to minus 1.75? I love the ability to do this in real time, so I can make these corrections. And again, it's going to be the same because this figure is symmetrical. So of course it's going to be the same, whether it's greater than or equal to 1.75 or less than or equal to 1.75. We're covering only 0.0401 or 4% of the population, right? See that? So 96% of the population is above this. Again, this is an extreme value. So we say this is the probability of our observed test statistic result given the null hypothesis is true. So our p-value is always stated with the qualification given that the null hypothesis is true, okay? Given our p-value is less than or equal to 0.05, this is the same wording as I had before, we would reject the null hypothesis that our sample mean is equal to the population mean. So alpha remains the same, whether we're doing left or right of the tail, right? Tail test, right? Doesn't matter. One tail test, whether it's left or right, alpha remains the same. In this case, the probabilities were the same, okay, because their z-values were basically the same, right? Except for one was negative and one was positive. Okay, imagine that our alternative hypothesis is now non-directional. We propose that our sample mean will differ from the population mean. As you can see there is no direction given. What's the probability that our sample mean is? Now, this is where it gets a little different. What's the probability that our sample mean is either greater than the population mean or lower than the population mean? So there's this either or scenario, and those of you who remember lectures on probability or means addition, So we calculate our Z statistic. Let's say we get basically their kids still ate 3.3 ounces of candy. So our Z value is still negative 1.75 with n equals 25 individuals. Our question becomes, what's the probability? This is the difference though, because even though we see that a result is negative, our question was an either or scenario. So now our question becomes, what's the probability that our Z value is less than or equal to 1.75 or greater than 1.75? Because we chose this non-directional hypothesis here. So even though we find something that's negative, it doesn't, we can't change things after the fact. Once we stated our hypothesis, it is what it is. So that's a probability that Z is less than or equal to negative 1.75 or Z is greater than or equal to positive 1.75. And we add these two together, right? Because that or means add. So it means we're looking at this area here or this area right here on the outside of the purple, right? And that equals 0.0802. We'll note that the area between the purple area between minus 1.75 and 1.75 is 0.9199. And the area outside is just subtracting that from 1, and we get approximately 0.0801. It's basically the same, 0.0802, 0.0801. Okay, so this is our area of confidence that our sample belongs to the population, the null population, and this is the area where we're not so confident, right? That's why we call it the type 1 error. Okay. Now, so by the way, look at this probability here. It's 0.0802. Given now our probability value is greater than 0.05, we would fail to reject the null hypothesis that our sample mean is equal to our population mean. So we cannot conclude that it's not equal. So basically, because we did, in this case, we did this, nothing has changed, right? We did a two-tailed versus a one-tailed test. You'll notice what happened was that we now fail to reject the null hypothesis. The exact same value that would have been significant if we did a one-tailed test, right? 3.3 ounces was significant with a one-tailed test when our one-tailed alternative was that our sample ate less than the population. The moment we do a two-tailed test, we fail to reject it. We say that a one-tailed test is more powerful than a two-tailed test. Power means the ability to reject a false null hypothesis. So you have more power when you do a one-tailed than a two-tailed test. So that's why it's better to choose one. But there are situations when a two-tail is better than a one-tail, when you're not really sure and you just started some line of research. A couple final notes here. When conducting a hypothesis test, our alpha value, as you saw, remains static. It's 0.05 if that's what we chose. Remember, alpha is your choice. So the heuristic is to choose 0.05, but you don't have to choose that. Just remember that. But you always have to justify why you do stuff, because most people are locked into this 0.05 and they don't want to choose something different. They think that's it, or else you'll get in trouble. The gods of statistics will throw thunder and lightning down at you. That's not true. So if we select the alpha 0.05, it's 0.05, whether we do one or two tail test. The only thing that changes is the critical value. And here's an example. In a one tail test, Z test, we have the critical value for a one tail test to the left of the mean, like where sample mean is less than mu is negative 1.45. It's a negative right here. See, it's negative 1.45. And one tail, so you see that's the bottom here, right? This is the Z value you'd find in a critical table. And for a one-tail test to the right, we have a Z critical value of 1.645. Again, they're symmetrical, right? Two-tail test, you'd have a Z critical value of 1.964, because we have to split our uncertainty into half. Now, here's the interesting thing, right? You'll notice that the critical value is further from the mean when we do a two-tailed test, it's 1.964, then we do a one-tailed test, it's 1.645. To reject the null hypothesis, our calculated value has to be further away from the mean, right, than the critical value. So what this shows us is that since the z critical value for a two-tailed test is further from the mean than when we do a one-tailed test, it becomes more difficult to reject the null. And again, that's another indication that we have more power with a one-tail than a two-tailed test. So here you just find a little explanation here, which is what I just talked about right now, but let's go through this. Note that when we use a one-tail test, our p-value is 0.05, right? 5% is at only one end of the distribution. When we have a two-tailed test, we split the uncertainty as we can commit a type 1 error in either direction. So that's the important thing here. You can commit type 1 error in either direction. So that could have a false positive result by saying that my sample mean is lower than the population mean or below the population mean, or I can commit a type 1 error by saying my sample mean is greater than the population mean. So I can do it in either of those two directions. And if we know from the rule of complementary events, well, actually, no, not the rule of complementary, excuse me. We know that the probability of either of two events occurring is the sum of their individual probabilities, right? So that's what happens here. So we have probability of two possibilities here. So either below that we commit a type 1 error below the mean or a type 1 error above the mean. So that's a probability of type 1 error below the mean plus the probability of type 1 error above the mean. So we add those together and we have a total alpha of 0.05, right? So we split the uncertainty. So again, this just makes our lives more difficult when we do a two than a one-tail test. But nevertheless, there's situations when you do both, right? One tail is better when you have a real clear indication of what's going on. So you're willing to gamble that you'll get it right. Two tail is better when you're not really sure. And the gambling doesn't really mean that much to you. Like when you're just starting a new line of research. Most statistical packages give you by default a two-tail test result. So if they gave me a two-tail test result, say like here, right, 0.0801, but I actually did a one-tail test, then I would just take this value and I'd divide it in half, and I'd get the one-tailed probability. A good way to remember how to do that is just to remember that the one-tail is always more likely to reject the null than the two-tail. So the one-tail probability is always going to be lower. It would be half of the two-tail probability. So that's the way I like to remember it. So if I was given a question in a test that says, if this is your two-tail probability, what's the one-tail probability? Just divide it in half. Conversely, if I give you a one-tail probability and I wanted a two-tail, multiply it by 2. Okay, and that's it. So I want to thank everybody for listening, and I hope this helps. This is something you just have to study. Okay, thank you. Bye.